Welcome to this 9th lecture of this course and also microwave filter design. So, we are completing almost the design. So, in microwave filter design, you see that up to this point we have seen the how to design RF filters with component values, lumped component values, but you know that those lumped component values lose their meaning if you go to higher frequencies. A capacitor can behave as an inductor can behave as an capacitor, etc., because those lumped elements, they are not of reliable values at high frequency. Also, it is difficult to make any value of lumped component at high frequencies, because here from the filter design, you for a specific insertion loss characteristic, you are designing a particular value, you are not sure whether that value, that lumped component is available or can be fabricated, because there can be fabrication difficulties. But we know one thing, that any lumped component you can fabricate by a transmission line, by a shorted or open transmission line, you can make any impedance value, because we know that in a transmission line the input impedance that behaves as a either as a tan function or a cotangent function. So, since tan function extends from minus infinity to infinity, plus infinity, and cotangent function also have minus infinity to plus infinity variation. So, any value, that means depending on the characteristic, choosing the proper characteristic impedance and the proper length, we can design any value of inductance or capacitance at high frequency. That is done with the help of a transformation called Richards transformation. We will first see P. Richards, if I remember correctly. P. Richards first introduced this transformation. So, they make this microwave filter replacing the lump component by stubs, transmission line stubs. Stubs may be open stubs or short stubs, as you all know, you have all dealt with that in your microwave classes. So, with Richards transformation we can attempt. What Richards transformation says, that you know that the input impedance of any transmission line with characteristic impedance Z0 and terminated by ZL, that is given by ZL plus J Z0 tan beta L by Z0 plus J ZL tan beta L. All of you know this, and we have also seen this. We have proved this also in the impedance transformer design. We have extensively used this quarter wave transformer, we have fabricated from this, etc. Now, you see that what Richard has done, he supposed that let us, this tan beta L is an important thing. So, let us have a mapping, that let us define a capital gamma, a capital this gamma, and that let us call it tan beta L ohm. So, tan beta L, and we know in a transmission line what is this tan beta L, where is the frequency? Frequency is inside beta. In transmission line, a distributed transmission line, the wave propagates by TEM mode. In TEM mode, this beta can be written as omega by Vp. Okay. So, you see that by this we are transforming the W plane to this gamma plane, okay, this capital gamma. So, now we assume then that in the new plane this gamma is the angular frequency. So, we can now write what happens to inductors ZXL. They will now, we will be calling, previously we were calling J omega L, now we will be calling gamma L, and that is what J. You see, instead of this I can say L is there, tan beta L, and in the susceptance P c, that will be calling So, how we are getting this? Let us see from this equation. This is his transformation. This is the result, that with this transformation, this is called Richards transformation, we get that the new values are like this, but let us see that what is this. So, again I write this Z in is Z naught Z L plus J Z naught tan beta L by Z naught plus J Z L tan beta L. Now, when you know that we implement an inductor by a short circuited stub of electric length L, electric length beta L, and we implement a capacitor by an open circuited stub of electrical length beta L. So, let us see those two first, that when we have shorted stub, shorted means the load side we short, that means Z L is equal to 0. So, what happens to the input impedance? This is like this, I have an Z naught, this equation is for terminating with Z L, now Z L becomes 0. So, what is my input impedance? This is my length L, here the propagation constant is beta. So, Z in will take the value Z naught, then you see that J Z naught tan beta L by Z naught. So, that will be J Z naught tan beta L. Now, you see Richards transformation shows that this Z for inductors it is to be J L tan beta L. So, I need to choose this Z naught as L. That means, to have to fabricate a J XL, that means an inductor with reactance XL, I need to choose what this stub, it will be a shorted stub with L as the characteristic impedance and length is L and its beta is given by that omega by V p. So, similarly, so this part we have proved that how Richard got this. Similarly, for let us do this thing again, write Z in is equal to Z naught Z L plus J Z naught tan beta L by Z naught plus J Z L tan beta L. This time let us put an open circuit, Z L is equal to infinity and this is Z naught, this is as before L, and also the propagation constant is beta. So, what happens? What is Z in value under this condition? Z in is Z naught, this is infinity. So, divide. So, you get 1 by J tan beta L. So, that is 1 by J tan beta L Z naught. Then I can write Z in is for capacitance, I know Z B C, that I can write as J C tan beta L. So, again it shows that I need to choose this as Z naught value as C. So, that is what he has done, that you see he has chosen a characteristic impedance of the line will be now be chosen as C and length is L. So, also for low pass prototype, you see low pass prototype, the cutoff frequency was omega c is equal to 1. So, in Richard's thing the mapping is to this omega plane. So, omega is capital omega is now 1. So, that is equal to tan beta L. So, this gives us what is the length L. Can I say that this implies beta L is pi by 4, because tan pi by 4 is 1. So, from that I can solve for L is equal to pi by 4 by what is beta? Beta is 2 pi by lambda, 2 pi by lambda. So, I get lambda by 8. So, it says that all these lengths, when we choose this, that this is the length L, these all lengths at omega c is lambda by 8. So, at the cutoff frequency the line, so I can say that when you are doing Richards transformation, this lambda is the wavelength at omega is equal to omega c. Now, obviously, this means that at other frequencies these lines, their impedances will change. So, the lump they will not represent the prototype lumped inductance and capacitance properly, but there is a periodicity that after every I have omega c, then at 5 omega c again the element values will match. This is because this beta L, the electrical length tan beta L, that is a periodic function of 2 pi, since I am having lambda by 8. So, I am having this variation that it is designed for omega c, at other frequencies it will not match, but at 5 omega c again it will match. Okay. So, filter response will differ at omega greater than omega c or omega less than omega c, those values it will be different, but that you can tackle by other techniques, by broadbanding etc., that are advanced techniques. So, now we can say that by Richards transformation in the low pass filter, if there was a inductance L, that you can represent by in a distributed circuit by a shorted thing. You take the characteristic impedance of the transmission line as L, same value, and this is lambda by 8 length at omega c. Similarly, a capacitor of value C, that with Richards transformation again the length is same. You see, that is the beauty, that all L C they will be of same length, but what is the value of Z naught? This will be 1 by C, and you make this open circuit, this is a short circuit. Now, since all these lengths are of same value, all the stubs are of same length, but they are of different variety, either short circuit or open circuit depending on a, these lines are called commensurate lines. So, you need not bother about these line lengths, and if required, suppose one length is not very small or very large, you can use this periodicity and go to higher values, so that higher or lower values, so that you can get that same thing. So, that means with this in the prototype design, whenever there is a lumped L or lumped C, you can represent like this. So, this is Kuroda's identity, but one more thing is that in high frequency another problem comes, that these lumped elements, suppose I have one L in a filter, then a C. Now, their distances, that also matters, because there is phase difference between them, when you are putting with this, then that distances etc., may not be feasible, and I need to sometimes I need to put some more gap or some less gap. So, some redundant line needs to be incorporated, so that these gaps etc., they become feasible, and there are sizable gaps between them, some match sections need to be put. So, more practical microwave filter implementation requires this, because sometimes I need to physically separate transmission line stubs. Then sometimes you see in fabrication, if I have this short circuit, open circuit, sometimes I need to make, for if there is a large circuit, that all the things should be short circuit or all the things should be open circuit, because that makes fabrication easier. But then I need to have transformation, that can be easily done, because any suppose I have implemented an inductor by a short circuit, now I can also implement that by an open circuit, because the equations are from equations I can have only the length etc., they will have different values. So, sometimes we need to do that, that is why this is another need for practical designs. Transform series stubs to short stubs or vice versa. That means, sometimes the opposite, some short stubs may be needed to change to series stubs. Then sometimes change impractical characteristic impedances into more realizable ones. Now, these three are the practical things. So, motivation for using another technique which is called Kuroda's identity. Kuroda's identity. Now, Kuroda, he gave these things. There are 4 Kuroda's identities. What he did, that suppose I have a lumped filter, I want to convert it to an inductor. That means, basically this shunt open circuit I want to make as a series short circuit stub. This is, so what he did, he said with this you add, let us say this was of impedance 1 by Z2, he said add a Z1. This in Kuroda's nomenclature it is called unit elements. This is a redundant element he is putting, and showing that this is equivalent to putting Z2 by n square, some line with characteristic impedance Z2 by n square, and then in series with a inductor of characteristic impedance n square. Similarly, this is called his first type, Kuroda identity first type. Kuroda identity second type is like this, that you have a series inductor, this is equivalent to, he says that you have this value is Z1. So, here is saying this is equivalent to 1 by n square Z2, this one. So, this is second type. Then third type is you have instead of an series inductor, you have a shunt inductor of value Z1. He said put with this a Z2, and that is equivalent to again Z2 by n square, then you want to keep all inductors, but then you need to have a transformer. So, this one is saying Z1 by n square, its characteristic impedance, and this is 1:n square turns ratio transformer, and his fourth variety is you have, it was a shunt, you have a series capacitance, then you put Z2, sorry, this is 1 by Z2, this is Z1. So, this he says this will be n square Z1, then you can retain this 1 by n square Z2, but then with a transformer whose ratio is n square is to n. So, in all these cases n square is equal to 1 plus Z2 by Z1. So, this each box, this represents an unit element, they are called unit element. Basically, it is same as a transmission line of unit element, all these are unit elements. All these are unit elements. These are all, what is an unit element? This is a transmission line of length lambda 8 at omega c. So, same as that what we have already seen the Richards transformation case, and the characteristic impedance in Richards transformation was L or C. Here characteristic impedance is as indicated in the identities. So, Z1 is the characteristic impedance of this box, Z2 is the characteristic impedance, Z2 by n square is characteristic impedance, etc. And lumped inductor and capacitor represent stubs of inductor represents a stub of short circuit and capacitor represents a stub of open circuit respectively. Now, all these can be proved, we will just see how to prove this first identity, let us say. So, first identity is, you see that I have basically, you see here I have a shunt capacitance. So, that means I have a shunt stub, open circuit stub, and this value is 1 by Z2 characteristic impedance. So, this stub 1 by Z2 and this length is that lambda by 8 length. This is a OC stub, and with this I have a Z1, again the length, all lengths here you see are L, which is lambda by 8, and this is my unit element. Now, this, if I have a transmission line of length L and characteristic impedance Z1, I know its ABCD matrix for this one, this particular one ABCD matrix will be cos beta L. This we have done earlier, that how to find ABCD matrix. So, in earlier NPTEL lectures you refer. Now, in terms of Richards transformation, I can, because there we have seen tan beta L is equal to the capital omega. So, 1 by root over 1 plus omega square into capital omega 1 j omega z1, then j omega by z1 and 1. Just you put all this you get. Then this is, remember, capital omega is tan beta L. With this I can write in this, and also this open circuited stub, what is the input impedance of this open circuited stub, that I can write as Z2 1 by J tan beta L, and that is in terms of this minus J Z2 by omega. So, now what is the, this thing is nothing but like this, minus J Z2 by omega. So, what is its ABCD parameter? ABCD will be simply 1 0 S21, you see, right, sorry, ABCD C will be Z2 and this is 1. This you can check that this one already we have seen earlier. So, now the composite, this whole thing, composite thing ABCD matrix will be multiplication of these two. So, I can write, first I will have, this is first, that means this into this ABCD, that is the beauty, these two are in cascade. So, I can easily write that 1 0 j omega by Z2 1 into 1 j omega Z1 j omega by Z1 1 into that scalar multiplier 1 plus big omega square. So, this is 1 by root over 1 plus gamma square, then 1 j Z1 j omega 1 by Z1 plus 1 by Z2 and 1 minus omega square Z1 by Z2. This is the, this left hand side. Now, right hand side you look at the first identity, the first unit cell, and then Z1 by n square. So, this I keep, this is basically LHS, I can say. Left hand side ABCD matrix composite is this. In right hand side I have this unit cell, length L, characteristic impedance Z2 by n square. Then just look at the figure, this is L and this is Z1 by n square. So, this is unit element, sorry, and this is short circuit series stub. So, I needed series stub. So, for unit element ABCD matrix will be 1 n square j omega n square by Z2 1 by root over 1 plus omega square. And for this one short circuited stub, again you see it is equivalent to this, that j omega Z1 by n square series stub. So, you know this ABCD matrix, its ABCD will turn out to be 1 this thing all we have done earlier, just refer there. So, the composite, so RHS will be composite of these. This is the first one into this one. If you do that, you get 1 by 1 plus square, then 1 j omega by n square z1 plus z2 j omega n square by z2 1 minus gamma square z1 by z2. Now, you see this is RHS, this is LHS. So, see LHS is this, RHS is this. So, on these two becomes identical only when I choose that n value, that n square is equal to 1 plus z2 by z1. That is why Kuroda has done that, and in all his cases this n square is 1 plus z2 by z1. So, with this you can now have all the permutations given, and so if you want to design any implementable filter up to Richards transformation you come, then you take the appropriate Kuroda's identity, because you see which one you need, because if you want to, if you have a shunt capacitance, but you want to convert to a series one, you can have this, just add this unit element and in series with that you can get it. Similarly, if you have this, you can use this. This is also popular, these two sometimes we use, but generally the inductance and A are not generally in this fashion, but in some band pass etc. there, but low pass high pass generally we have this type of thing. So, you can use these two identities, but if you can refer to here and always do this. So, we will see some implementation of this in the next lecture, that how we go about these transformations. Thank you.